Hi everyone, let's continue the second part of the CORDIC chapter. In the first part of this chapter, we have implemented the CORDIC algorithm in C. But if the variables are in floating point, the loop carry dependency caused the II to be 15. So to solve this problem, what we're going to do today is reduce the complexity of the computation by changing the variables to be a fixed point representation. Today's learning objective is to optimize the baseline CORDIC implementation, and you'll be able to explain the fixed point and floating point representations. And we're going to compare the hardware costs for using fixed point and the floating point representations. When I say fixed point representation, some students seem to think that it's a matter of changing the floating point variables to int or short variables. Well, let's see if that's true. Please change the data type and the cosine sine type to int or short types and run synthesis again. This is the synthesis result of the float type we saw in the last class, and this is the synthesis result if we change it to int or short types. You can see that the flip-flop and the luck consumption is much less than the float type, which is good. But the problem is that II is still 3, much less than 15 we saw in the last time, but it's still larger than 1. If we look at the synthesis log, the reason is pretty much the same as before. It is due to the loop carry dependence on variables current sign, data, and factor. You know, it's good that the II reduced from 15 to 3, but it's not quite there yet. So let's try to optimize the C implementation so that we can bring it down to II equals to 1. This is the baseline implementation we saw in the last class, and there was a loop carry dependency on variables current sign, data, and factor. There isn't much we can do about current sign and data, but for factor, notice that it is being divided by 2 each iteration. This means that we know what factor is going to be after j iterations. So let's get rid of factor and replace it with the right shift by j. You see that the factor is only used on the cosine shift and sine shift variables, so we only need to shift on these 2 places. Next, let's get rid of multiplication. We already removed a variable factor, so we only need to get rid of a sigma as well. Sigma is either -1 or +1. So depending on the value of data, the variable cosine shift becomes either a plus or minus cosine shift, and the variable sine shift becomes either minus or plus sine shift. And that's why down here, I replace sigma with the ternary operator that either subtracts or adds sine shift and cosine shift depending on the sign of variable data. Okay, let's see what happens if we make these code modifications. This is the synthesis report after the code changes. You see that the II is now 1, which is the result we wanted. Alright, now that the performance is satisfactory, let's check if our code transformation is correct with the test bench we made in the last lecture. As I explained before, you need to run C simulation and check the correctness every time you make some kind of code modification. Now, a slight difference from the FIR project is that the CORDIC algorithm inherently has some error depending on the number of iterations. So you can't expect the output to exactly match the golden output. So as long as the error is at a similar level, you probably have made the correct modification. So let's make 3 versions, one with the float type, another with the int, and another with the short type. If we measure the RMSE, which means squared error, and the maximum error after running 5 iterations on the float version, you see that it is 0.0245 and 0.0627. But if you do the same measurement with the int or short type, it is 0.707 and 1.0. Considering that the maximum value of cosine and sine is 1.0, it seems clear that the int version and the short version is producing an incorrect result. So this suggests that simply changing a variable type from float to int or short is probably not the correct way of adopting fixed point representation. So let's take a step back and ask ourselves, what is fixed point representation? Right? So only after answering this question we'll be able to do fixed point optimization. So fixed point representation is a way of representing a number with a fixed number of digits before and after the radix point. It is composed of 3 components: sign bit, integer part, and the fractional part. The length of the integer part is called the integer word length, or IWL, and the length of the fractional part is called the fractional word length, or FWL. And the combined length of the sign bit, IWL, and FWL is called the word length, or WL. Okay? Let's see an example. Please represent 8.5 in decimal number, or 1000.1 in binary number, with 1 sign bit, 6 integer bits, and 1 fractional bit. So this is a positive number, so we can put 0 as the sign bit. And then put down the integer bits. Integer 8 requires 4 bits, 1000, and since the IWL is 6 bits, we can add extra 2 zeros before writing down 1000. And finally, we can put down the fractional bit 1. Okay? Next, if sign is 1 bit, IWL is 5 bits, FWL is 2 bits, the fixed point representation is now going to be 001, 000, 10. So in this case, FWL is 2 bits and it's longer than we need. So we simply add more 0 at the end. So depending on the IWL and the FWL, a same number can be represented in a different way. Okay? Now let's see how a negative number is represented in a fixed point representation. We typically use 2's complement. Remember from your logic design course, where the negative number is obtained by flipping all bits and adding 1. Right? So -3 is flipping all bits in +3, 1, 0, 0, and adding 1. So 1, 0, 1. And if you have 3 bits, you can represent from +3 to -4. Okay? The fixed point representation has a limited number of digits for the fractional part, so we sometimes need rounding. Let's think about the case where we are reducing the FWL from 2 bits to 1 bit. There are several rounding schemes you can choose. The easiest scheme for hardware implementation is rounding to negative infinity or simply rounding down. In this scheme, you just need to truncate the unneeded fractional bits. For example, if you have a 3.75, you can get rid of the last fractional bit, and after rounding, it'll become 3.5. Note that there are other rounding schemes like round to positive infinity or round to nearest even. Now let's think about the arithmetic in fixed point. Suppose that there's no sign bit, IWL is 4 bits, and the FWL is 4 bits. And we're going to add numbers 8 and 0.1875. Let's first convert these numbers into a binary representation. Since the IWL is 4 bits, number 8 is going to be 1000 without any leading zeros in the front, and we're going to put 000 for the fractional part. For 0.1875, we'll put 4 bits for the integer part and 0011 for the 0.1875. There's no leading zeros at the end because the FWL is 4 bits. The added result is going to be you just add these numbers together, and it'll be 10000011. So if you convert this number back into a decimal number, it's going to be 8.1875 as expected. Let's take a look at another example. In this case, we have one sign bit, 7 bits of IWL, and no FWL. And we're going to add -8 and 3. Let's first convert -8 into binary representation. So positive 8 is 00001000, and if we're converting this number into a negative number, we just flip all bits, right, and add 1. So -8 is going to be 11111000. So in binary, -8 plus 3 is going to be 11111000 plus 00000011. So the result is going to be 11111011. And if you convert this back into a decimal number, you can check that this number is actually -5 as expected. Okay. So if you need some time to go over these numbers, please pause the video now. Otherwise, please proceed to the next slide. We've seen many different fixed point representations so far, and you probably noticed that the word lengths can be of arbitrary length. So C++ default types of int, short, and the character, it may not be enough, and that's why Vitis HLS provides ways of customizing the fixed point representation. There are 2 ways. The first one is the AP fixed class, and you need to include the AP underscore fixed.h header, and the type is defined as AP underscore u fixed bracket word length and integer word length. The fractional word length is obviously going to be WL minus IWL. And if you initialize variable a in this way, then the value 4.0 is going to be stored in the format you just specified. And if you want a signed number, you can use the AP fixed type. Okay. Another class you can use is the AP int class. You need to include the AP underscore int.h header, and in this case, you can type AP underscore u int bracket word length. This is for the unsigned number, and if you want a signed number, you can just type AP int WL. Okay. Now, notice that you do not specify the IWL and the FWL for the AP int class. Actually, in this case, it's up to the programmer to manage IWL and FWL. Okay, and we're going to see some examples of doing this in the next class. Okay, so now let's do some practice in fixed point arithmetic in the next slide. Suppose that a variable has a sign bit, IWL is 4 bits, and the FWL is 3 bits. Please compute minus 3.75 plus 1.125. The answer is obviously going to be minus 2.625, but your task is to do the computation in the given fixed point representation. Okay, so please pause the video now and write down the intermediate equation in binary. Let's see the solution. 3.75 is 11.11 in binary representation. So if we convert into this format, we're going to assign one sign bit, so it's going to be 0, it's a positive number, and IWL is 4 bits, so 11 is going to be 0011. We added 2 leading zeros because it's a positive number. And then we add the FWL 3 bits, so there's only 2 bits here, so we add 1 0 at the end, so it's going to be 110. So the whole number is going to be 0001 1110. Okay, and negative 3.75 is we've done this before. We flip all bits from this one to this one, so it's going to be 111000001 plus 1. So minus 3.75 is 11100010. And 1.125 is going to be, we first converted into a binary representation, 1.001, and then we add the sign bit 0 and 3 bits of IWL because there's only 1 digit here, so it's going to be 0001. And for the FWL, we just write down these 3 numbers, 001. Finally, we do the computation. We add this number and this number, which just came here. And if we add these 2 numbers, it's going to be 1110, 1011. Okay. And if you convert this number back into a decimal representation, you can check that it's minus 2.625. Okay. Now we'll learn about the floating point representation. Floating point representation is defined by this IEEE standard, and there are 2 representations. The first one is the single precision floating point, which is 32 bits long, and the second one is the double precision floating point, which is 64 bits long. In C, this one is the type float, and this one is the type double. Let's look at the format of floating point representation. The first one is the sign bit, and then comes the exponent field. In single precision, it's going to be 8 bits, and for the double precision, it's going to be 11 bits. The last field is the significant, also called the mantissa or the fractional bits. It is 23 bits for the single precision and 52 bits for the double precision. The value of a floating point can be computed as -1 to the power of sign times 1 plus significant times 2 to the power of exponent minus bias. The bias value is 127 for single precision and 1023 for the double precision. Okay, notice that since the floating point representation has a dedicated field for the exponent, floating point can represent a large range of real numbers, compared to the fixed point representation. Let's see how to do floating point addition. The floating point arithmetic is not the main focus of this lecture, but I'm still showing it to you to demonstrate how complex it is compared to the fixed point arithmetic. So let's compute 1.11 times 2 to the power 1 plus 1.10 times 2 to the power minus 1, which is same as adding 3.5 and 0.75 in decimal numbers. So the first step is to align the binary point. You see that these two numbers have a different exponent, so we should align them to the exponent of the bigger number, which is this one. So we're making this into power of 1. That is, we're increasing the exponent by 2 and right shifting the significant by 2 bits. Then the significant will become 0.011. The next step is to add the significant. 1.11 plus 0.011 is 10.001, and you can keep the exponent as is. Next, floating point number is required to have 1 as the integer. So if you have a 10 as the integer, you need to normalize. So we have to move the binary points and like this, and instead increase the exponent by 1. In the beginning, we had 2 fractional bits, right? So we have to do a rounding at the end to keep it down to 2 bits. And after rounding, this is the final result. Now we have seen all the steps needed to do floating point addition. You can see how complex it is compared to the fixed point arithmetic. There's so many operations needed. So the point I wanted to make is that the floating point operation is very costly in terms of hardware, speed, and power. Let's do some quantitative comparison of the resource consumption between floating point representation and the fixed point representation. As an example, the cost of an adder is shown in the tables. An adder for a float type needs 2 DSPs, 325 flip-flops, and 206 lookup tables. And the adder for an integer type needs 39 lookup tables. And the adder for a short type needs 23 lookup tables. So it's pretty obvious that the float type adder consumes the most resource. Okay, one thing you might not be familiar with would be the DSP. I'll explain it in the next slide. DSP, or DSP48 to be more precise, is a dedicated multiply and accumulate unit on FPGA. It's composed of a 27-bit times 18-bit multiplier, 27-bit adder, and a 48-bit accumulator. So it's definitely a computation unit. And DSP48 can be used for both fixed point and the floating point operation. For example, if you're multiplying a short type by a short type, it's going to consume 1 DSP. And if you're adding 2 floating point numbers, it's going to consume 2 DSPs as we saw in the last slide. Okay. Now, note that it's possible that the number of DSPs consumed might change when the operator is pipelined. Anyway, so if your kernel is consuming some DSPs, it means that it is consuming a considerable hardware resource for computation. All right, so let's look at the synthesis reports we saw earlier in this lecture. Changing a float type to int or short reduces the DSP, flip-flop, and the lock consumption by a lot because fixed point operators are much simpler than the floating point operators. But we also saw that simply changing float type to int or short type leads to wrong result, right? And now we know the reason. This is because we have not set the IWL and FWL variables while making the fixed point conversion. So the output is going to be incorrect. So the next question is, how do we assign IWL and the FWL systematically? And this is what we're going to learn in the next class. In fact, we'll go over the whole fixed point optimization process the next time. Here's today's summary. We have optimized the CORDIC algorithm by removing locality dependency and replacing multiplication with the shift and additions. But we also learned that simply changing a variable type from float to int or short is not the correct way of doing fixed point conversion. So as a starter, we learned the fixed point and the floating point representations and their arithmetic, and also that the floating point representation has a larger dynamic range than the fixed point representation, but consumes more resource. And we're going to pick up where we left off today and learn the entire fixed point optimization process in the next class. So see you then.